Okay, let's now do another example here. So you see here, concentrated sulfuric acid, a very powerful and strong acid, is 96% H2SO4 by mass. So the remaining 4% is water. So this is an example of concentration where um, we say we have a weight percent, which equals um, 96. Like we essentially say 96.0 grams H2SO4 over 100 grams of solution. Okay, where 4.00 grams is water, and so when we add the two together, H2SO4, we get 100 grams solution. Okay, so if we multiply this by percentage, we will get 96% H2SO4. So that's another way we represent concentration is by percent. So those are the two most common ones: weight percent, volume percent if you're doing liquids, and then sometimes we have mass volume percent as well. So we can also have volume percent and what we call mass volume percent. So mass volume percent is an example where you dissolve, for example, 25 grams of, say, a solute, and you fill a solution up to, like, say 250 milliliters. So then you would divide those. You would divide those, and you'll get a mass volume percent. Even though the units won't cancel out in this case, we just assume that there's no units in this case. But you see here in weight percent, the units would cancel, so you don't have any units at the end. Okay, anyway, so here is a diagram illustrating what we mean by our solutions here. So on exams and stuff, I encourage you, if it does help you, please use pictures. Pictures, are worth 1,000 words. They can definitely help support your answer if you think it's helpful. But they are not necessary. So drawing is not a requirement for this class. Okay, so first we have so we need to calculate the number of moles of sulfuric acid in a 1 liter of concentrated sulfuric acid. Okay, if the density of the solution is 1.84. Okay, so let's go over that. Okay, so you may say, oh, why do we have to use the density? Well, we want to when you have a percent, when you're given concentration in percent, you need to use the density to figure out the moles. So that's one of the downsides of using percent solutions, is that you would need to know the density of your solution. Okay, so first things first, let's convert our units to cubic centimeters, because if you look in this picture here, we have our density here, 1.84 grams per centimeters cubed. So centimeter cubed is the same as a milliliter. So we know that one liter is equal to 1,000 milliliters, and we know that for each milliliter, that would fill the a square of 1 cubic centimeter of what. So if we fill a square, that's 1 centimeter on all sides of a cube. So that's the definition of a cubic centimeter. Basically, the volume of a cube that's 1 centimeters cubed will be filled up to 1 milliliter. So that's the definition of a cubic centimeter. It's another unit for volume because it has 3 dimensions. So length, width, and a height. So in this case, we have 1,000 cubic centimeters. Okay? So 1,000 cubic centimeters. Okay, so now we have cubic centimeters. We have the total volume of solution, right? So now we can use the density to figure out how much of that is grams of sulfuric acid. So we take 1,000 centimeters cubed times 1.84 grams per 1 centimeter cubed. So we want to arrange our conversion factor where our centimeters cubed would cancel out, so we treat them as a variable. Okay, so the centimeters cubed would cancel out, and what we get here, sorry, I should have drawn this a little bit differently. Okay, and then we get 1.84 times 10 to the third grams H2SO4. So that's a lot of H2SO4 in 1 liter. So that's going to be a very strong acid solution here. Okay. All right. Now we know the mass of the solution and the total mass of the solution. We can calculate the mass of H2SO4 directly. Oh, so sorry. It wasn't actually H2SO4. It's actually solution. So this is the mass of solution. Okay, so this is actually the mass of solution that we have in total. So now that we have the total mass and we know that our solution is only 96% H2SO4, we can now figure out how much of that mass is exactly sulfuric acid. Okay. So 1.84 times 10 to the third grams solution. Okay. And we know that from our percent, 96 grams H2SO4 is present in 100 grams of solution. So if we carry out that calculation, gram solution would cancel out, and we get slightly less than what we started with, because it's only 90. It's 96%, so we're going to decrease a little bit here, but not by much. So these chemical calculations, they always require some careful thought, and there's a lot of steps often in these problems. So these steps here will build your kind of like problem solving skills, especially when dealing with chemical reactions and chemical concepts here. So it's okay. It's helpful that we kind of think these through here and just take it step by step and don't rush to any conclusions right away. Okay. Good. Okay, so now let's convert mass of H2SO4 to moles. So lastly, we'll convert H2SO4 to moles. Okay. So 1.77 times 10 to the third, not negative, third grams H2SO4. So if anyone's wondering what we use sulfuric acid for, it's in your car batteries. It's used as a car battery, so it's used as a chemical reaction to generate electricity for your car. And it's used in chemical industry as a popular acid catalyst for many reactions. So is a very important um, industrial chemical. Okay, so 1 mole of sulfuric acid is equal to, for the molar mass of sulfuric acid, please just recall that, just look up the molar masses of all the elements, and you should get 98.1 grams H2SO4. Okay? Okay, so if we do that, we get 18 moles of sulfuric acid per liter of solution. So that's 18 molar. So that's very concentrated. So concentrated is anything above 1 molar, that's considered concentrated. So anything above 1 molar, that's considered fairly concentrated. Okay? So, and if we think about this, 18. So we have 18.0 moles of sulfuric acid. If we divide that by 1 liter, that gives us 18 molar. So that's very concentrated. So very concentrated. Very concentrated. Okay. So that's concentrated sulfuric acid. So sulfuric acid is pretty much almost pure. Almost pure is almost 100%. So it's very pure. Sulfuric acid by itself is almost very is almost 100% sulfuric acid. So as opposed to other acids like concentrated HCl and like HBr or HI, where they're like just a kind of like a certain percent of purity. Sulfuric acid is nearly 100%, so it's very, very concentrated. Okay. All right. Checkpoint here. Why do chemists find it more useful to describe concentrated H2SO4 as a solution that contains 18 moles of solute per liter instead as a solution that is 96% sulfuric acid by mass? Okay. So, thing to keep in mind is that generally it's easier to use molarity percent by mass requires a conversion to moles. Okay, so if we go back here, this calculation took 1, 2, 3, 4. So this took 4 steps to calculate moles. And if we compare this to this calculation before, you see when we have molarity, it was just a single step, right? It was a single step. So compare that to 4 steps for percent, because here we have the volume, right? We have the volume and we have the concentration. Just like in this example, we have the concentration and the volume here. So given that molarity only took us 1 step or 1 calculation to figure out the moles, percent by mass took us 4 steps to figure out the moles. So we like using molarity better, but percent by mass is still very useful for other applications, maybe in biology. Well, biology, they like to use some other stuff too, like osmolarity, molality, but typically speaking, molarity, chemists like using molarity the best. Okay? And that's why we're studying it so diligently here. Okay, let's move on to the next part of this lecture. Okay, so now we're going to talk about dilution calculations. Okay, so see here, we have a, you see right here, we have a flask, we have two volumetric flasks here. We're going to take a known amount of the solution from flask 1 and transfer it to new flask 2, and we're going to dilute it to a new volume. Okay, so that's how we change concentrations typically in chemistry. So we can go down in concentration, but typically in the lab we can't go up in concentration without making a new solution. Okay, so it's not easy. So we can't control the concentration. If we try to increase the concentration, we can't control the new concentration, because if you try to evaporate something, right, it's hard to control the volume because you can't really control the speed of evaporation with precision or accuracy. Okay, so but we can dilute things pretty easily because we just take a known amount of the first solution in flask 1, and then we just add it to a second flask and dilute that to a new volume. So those are factors we can control easily. But we can't control concentrating solutions or removing solvent. Because if you just remove a part of the solution, say you want to remove some of the solution, right? Well, the concentration doesn't change because the solution is uniform. So when you take out a known volume of solution, you're also taking out the solute as well. So we can't just remove solution to concentrate things. We have to make a new one by using more of the original solute to increase the concentration. So we're only concerned with dilution here. So dilution calculations. Okay. So adding more solvent to a solution to decrease the solute concentration is known as dilution. So when you make some orange juice, add some water, the intense orange flavor, sour, tangy orange flavor will go down, right? And it becomes more drinkable and more enjoyable. So a refreshing beverage, right? So if we know the molarity and the volume of solution, we can prepare a more dilute solution of any concentration. So it has to be dilute. When I say any desired concentration, I mean it has to be lower than the concentration you started with. It can't be higher. Okay? So this general equation should be memorized and dedicated to memory, but I would give you the equation. When you're in lab, you kind of want to make sure you understand this when you're doing stuff in lab, so you can, so you're not kind of lost and you don't do something wrong in the procedure. Okay, so generally speaking, for any type of dilution, we can say the concentration of our first solution multiply a known volume of that solution will equal the concentration of the second solution, the more dilute solution, or multiplied by the new volume of that solution. Okay, so for example, say we have, say we know the volume of. We know the volume of our desired solution, and we know the desired concentration we want, and we know the concentration of our first solution. We need to figure out, okay, how much volume of concentration 1 do we need to take out and dilute it to a known volume V2 to get our new concentration C2. So that's how you kind of use these equations, but we'll go over that in some examples, okay? We can also write this as CI, or concentration initial solution, volume of the initial solution, and then CF, or V n times VF, which is the concentration of the final solution and the volume of the final solution. Okay. So in this case, V2 and C2 is the final concentration of the newly diluted solution. V2 and VF is the new total volume. We can actually simplify this in the units of molarity here. So here's a dilution equation. M1 V1 equals M2 V2. That should ring some bells because that's called the dilution equation. So one thing I want to keep in highlight, I boxed this for a reason because this is a very important equation you should know, everyone should know. This equation states that no matter what, the number of moles remains the same in both the diluted and undiluted solutions. Okay? What changes is the ratio of moles of substance to the amount of solvent. Alright? So what that means is, if we take a look here back in our picture, so the number of moles of manganate ion per manganate ion in solution remains the same when the solution is diluted. So what does that mean? It's the same. Okay. So for example, the moles of solute removed from the initial solution with the pipette are going to be the same mole of solute found in the final solution. So it doesn't mean I don't mean the total number of moles in both solutions are equal. That's definitely not the case. But what I mean is that when I take a volume from flask 1, right, there's going to be some moles of solution in my pipette, right, I put some of the first solution in the pipette, right? So when I add that to flask 2, the number of moles in the flask now are going to be equal to the moles that were taken up in the pipette. So even though I dilute it with water, the moles remains the same. The number of moles remains the same. Okay? So that's what that is talking about. The intensity of the solution will decrease though. So you have a concentrated solution, you add more water, you see the intensity of the solution fade over time or decrease as dilution goes up, and that's because the solution becomes more dilute. The colored substance is not as dispersed in solution, so it's going to be surrounded by more water molecules, therefore it can't interact with light as much, so that's why the color decreases. Okay? So one thing we want to keep in mind in this picture, right here, number of moles, MnO4 minus is equal number of moles MnO4 minus in the flask 2. Okay, so the number of moles that were in pipette are going to be equal to the number of moles that is transferred into flask 2. So it doesn't mean that the two solutions here, so flask 1 and flask 2, it doesn't mean that they both have the same number of moles. That can't be true, right? Because one is of a higher concentration and one is of a lower concentration. But the amount of moles that you took out of the pipette and transferred into the flask 2, those will be equal. So on both sides of the equation, really, whatever volume you take out in a V1, the number of moles will be same on both sides of this equation. So no matter what, the number of moles remains the same in both the diluted and undiluted solutions. Okay, so in the next video, we'll talk about using this equation. Okay, so see you then.